All right, let's jump right into this explainer. We are currently looking at an absolutely massive, fundamental paradigm shift happening right now in the world of agentic AI. If you've been following this space, you know the ultimate holy grail has always been creating an AI that can use a computer exactly like a human does. But let's be real, the reality hasn't quite matched the hype. Well, until now. Today, we're dissecting the source material behind a literal game changer, Standard Intelligence and their FDM-1 model.
Let's start with a question that kind of exposes the dirty secret of the AI industry. Why do today's most advanced AI agents completely lose their minds after just 6 seconds of computer use? I mean, you've probably seen those slick demos of an AI clicking a button or filling out a basic web form, but if you actually ask it to do a long horizon task, say setting up a complex software environment or doing an hour of heavy financial modeling, it just breaks down. It gets stuck in endless loops and completely forgets what it was doing.
Section 1. The context bottleneck. The limitations of screenshot AI. To really understand the solution, we first need to figure out why this bottleneck even exists.
So, looking at the recent history of agentic AI, there's a clear trend that perfectly shows why progress just hit a wall. Back in March 2023, we saw basic tool use introduced with GPT-4. By October of that year, Anthropic launched their Claude Screenshot API in beta. Fast forward a bit to November 2024, and Claude 3.5 Sonnet gave us a public release for computer use. But do you notice a trend here? Up until early 2026, the entire industry was heavily relying on static images. The AI would essentially take a screenshot, look at it, decide to move the mouse, take another screenshot, look at that, and so on. It was incredibly clunky. But then, in February 2026, Standard Intelligence published FDM-1, which was this massive, video-native leap that completely ditched the screenshot approach.
The difference between these two approaches is honestly night and day. The traditional AI paradigm relies on humans manually annotating all those screenshots. And because human annotation is just so painfully expensive and slow, the absolute best open-source datasets maxed out at less than 20 hours of training data. That directly resulted in that fatal 6-second context limit we just talked about. But FDM-1? It abandoned screenshots completely. By processing continuous 30 frames per second video, they trained this model on a staggering 11 million hours of data. The result is an unbroken 2-hour context window. It's literally the difference between flipping through a clunky old flipbook and sitting back to watch a high-definition movie.
Section 2. The $75 million startup, the David versus Goliath metric. Now, tackling a bottleneck of this magnitude usually requires the endless resources of a trillion-dollar tech giant. But that's not what happened here. Let's look at the paradox of the startup that actually cracked this code.
6. That's it. That is the total number of people on the team at Standard Intelligence. Just 6 people.
And somehow, this tiny 6-person team just raised an astonishing $75 million. We're talking backing from massive industry heavyweights like Sequoia Capital, Spark Capital, and Andre Karpathy, the former AI director at Tesla. Which brings us to this jaw-dropping number of $500 million post-money valuation. To put that into perspective, in the 2026 AI market, this proves that pure talent density and a fundamental architectural breakthrough are far, far more valuable than just throwing thousands of engineers at a broken screenshot paradigm.
Section 3. Decoding the FDM-1 breakthrough. How to train on 11 million hours of video. Okay, let's dive into the technical magic that made this entire David versus Goliath story possible. How exactly do you pull this off without spending billions on human labelers?
Well, the secret sauce here is the inverse dynamics model, or IDM. Let me put this in plain English for you. Normally, to train a computer use AI, a human has to sit there, record themselves using a computer, and meticulously write down, okay, I moved the mouse here, I clicked this button, I typed these exact words. It is agonizingly slow. The IDM flips that entirely on its head. It's a neural network that just watches raw, unlabeled video of a computer screen and automatically reverse engineers what the human did. It sees a change on the screen and instantly predicts the action that caused it. This completely removes that massive bottleneck of expensive human annotation.
So, let's break down how they put this into practice across a 3-step pipeline. Step 1. The IDM takes a baseline of 40,000 hours of contractor video and automatically labels it. 0 manual human tagging required. Step 2. Because that labeling is now fully automated, they can scale the data set up dramatically, churning through 11 million hours of raw video. To put that in context, this dataset is literally 200 times larger than the next best open-source alternative. Finally, step 3. They take all that perfectly labeled data and use it to train the Forward Dynamics Model, or FDM-1. And unlike the previous model, this one doesn't look backward, it looks forward.
It predicts the absolute next best action for the AI to take in real time at a buttery smooth 30 frames per second.
But all that data means absolutely nothing if the AI's engine can't process it efficiently. Think of the video encoder like the engine of the AI itself, and the disparity in performance here is staggering. A traditional vision language model encoder burns through a budget of 1 million tokens in just 1 minute of video. It's a complete gas guzzler. But look at the FDM-1 encoder. On that exact same 1 million token budget, it can process 2 full hours of video. It boasts a 100x faster convergence rate compared to baseline vision transformers. It is a stunning, paradigm-shifting leap in token efficiency.
To really anchor just how unprecedented this is, check out this quote from a piece published in SiliconANGLE on April 30th, 2026. They wrote, "Standard Intelligence's encoder enables models with a context window of 1 million tokens to process 2 hours of 30 FPS video per prompt. This isn't just some minor incremental update. No, it is a 100x efficiency breakthrough that fundamentally rewrites the rules of compute costs for AI agents."
Section 4. Real-world agentic applications. Unlocking long-horizon workflows. So what does a 100x improvement actually allow the AI to do out in the wild?
Well, as you'll see, FDM-1 goes far, far beyond just simple scrolling and clicking. Look at these concrete use cases. First off, it can execute autonomous multi-hour 3D CAD modeling sessions. Just imagine an AI designing incredibly complex metal components from start to finish without breaking context or getting lost. Second, and honestly, this is wild, it learned to drive a real car through a web interface after just 1 hour of fine-tuning. Because it actually understands continuous video, it can map interface controls to real-world physics. And third, it is fully capable of running automated software vulnerability fuzzing and security scanning at a massive scale. It can seamlessly navigate complex code environments for hours on end to track down hidden flaws.
So if you take only one thing away from our explainer today, let it be this. The transition from screenshot AI to video-native AI is absolutely the defining infrastructure shift of 2026. Standard Intelligence realized that trying to teach an AI to use a computer by showing it a slideshow of screenshots was basically a dead end. By moving to continuous video and solving the data bottleneck with their inverse dynamics model, they've finally unlocked the true potential of agentic AI.
And that leaves us with this final provocative thought. We've seen it design complex CAD models, fuzz software, and even drive a real car. When AI agents can watch and learn from 11 million hours of video, what human workflow will they master next? The long horizon barrier has officially been shattered, and the possibilities from here are wide open. Thank you so much for joining me for this explainer. I really hope this helps you structure your understanding of the incredible leaps happening in AI right now. Keep learning, and I'll catch you next time.